early detection of functional corner case bugs using methodologies of the ISO 26262. Abstract. ISO 26262 does not suggest a new verification methodology for systematic failures covered in design verification. However, ISO 26262 requires a persistent impact analysis and a risk assessment at every stage. So we introduced HARA, Hazard Analysis and Risk Assessment, and Safety Analysis methodology used in ISO 26262 to the design verification field and used it to measure the risk of each element of a target design. We found risk factors that can present the level of the risk for detailed items, and through the FMEA, failure mode and effect analysis, and DFA, dependent failure analysis, DFA, and it was possible to easily see the expected design vulnerabilities by classifying the risk factors that could affect the system level. And to verify the expected design vulnerabilities, a systematic fault model was created using the ML algorithm. Through this, it was possible to verify the time-critical corner case, which has been difficult to in pre-silicon so far. In the introduction, the biggest change around us in recent years is probably the automobile sector. This is because the supply of the electric vehicles is expanding, the high-performance semiconductors and various advanced technologies are being integrated for complete autonomous driving, steering, and braking systems, which are core functions of the automobile, are already electronically controlled through built-in microcontroller. In the future autonomous driving era, the driver's role will also be replaced by the sensor and artificial intelligence. However, the number of accidents due to the instability of electronic devices is also steadily increasing. This is because even a minor error that can be solved by a simple rebooting in our mobile phone can threaten the life of the driver if it occurs while driving a car. ISO 26262, an international standard for automotive functional safety, has been published to prevent damage caused by the malfunctioning of such automobile functions. ISO 26262 provides a clear standard for safety to be considered when developing functions that can be directly related to human life, and provides specific guidelines for effectively reducing risk due to the increase in technical complexity. The ISO 26262 classifies the causes of the risk into systematic failures and random hardware failure. Systematic failure is a failure that arises from the activity itself that develops and produces a system. Human error of personnel participating in developing and production activities is the biggest cause. Artifacts caused by the incorrect design in the semiconductor design process are typical systematic failures. Random hardware failure is a term that is limited to the hardware element and refers to the failures that occur due to the physical limitation of a hardware element. This occurs mainly in the form of memory cell deterioration and instantaneous state change of logic caused by external environment factors and is not covered within the design verification stage. In other words, in order to ensure functional safety in ISO 262, the following two requirements are required in the semiconductor design verification stage. The first one, avoid or prevent systematic failure by checking all errors in the design process. Number two, even if systematic failure occurs, there must be a plan to minimize the impact on the system. ISO 26262's design verification requirement for systematic failure are different from other fields. However, in the automotive environment covered by ISO 26262, a higher level of the strict reliability is required than before because even a minor error can threaten human life. And these high-level requirements of ISO 26262 are also affecting the semiconductor development process in other fields. Semiconductors are already expanding their scope of use from a wall for human convenience to a variety of fields where human safety must be ensured. Accordingly, higher reliability than before is required in the entire semiconductor field. So in this paper, we created a methodology called Systematic Failure Analysis, SFA, for semiconductor design verification by referring to the safety analysis methodology of ISO 26262 and to verify the failure mode with the complex conditions. The ML-based PSS action sequence model announced last year was applied. Our methodologies used the methodologies proposed in ISO 26262, but were made to be used to increase the reliability of the design verification stage in the general semiconductor field. At the end of this paper, we will also show how our result can be used again in ISO 26262. Two, systematic failure analysis. ISO 26262 relies on the traditional design verification methodology to mitigate the risk due to the systematic failure. However, as system complexity increases, errors caused by the unintended action that occur during interaction between different components are increasing. As a result, fatal systematic failures with complex interaction conditions that are difficult to detect with existing verification methods are often found at the silicon level. In order to prevent this, it's necessary to identify the function and critical sequence in which such a corner case can occur in advance and predict the risk. For this reason, we created a systematic failure analysis SFA to extend the functional verification coverage by restricting risk factors from the IP level and predicting risks. Failure mode definition. Failure mode is created to predict possible failures during the function operation of the semiconductor component and to establish preventive measures against them. The failure mode created during design verification for SFA records the expected failure when a fault occurs due to the following causes during function operation. In SFA, failure mode is used as a verification target to ensure that it does not occur. The FM1, integrated issues, connection configuration. FM2, accessibility issues, access path, access control. FM3, functionality issues, roll out unintended behavior. FM4, state transition issues, power gating, clock gating reset. FM5, absence of independence, or FFI, freedom from interference. An example of the failure mode of SFA as follows. The table 1, example of the failure mode. ID IP function failure mode, there are so many. Okay, next time. Yeah. Among the types of the failure modes above, SM5, absence of independence, or FFI, freedom from interference, is an item related to the functional corner cases that could not be verified in the existing design verification. Because this occurs due to interference access from the outside that occurred at a specific point of weakness in the function, it was difficult to reproduce in the existing verification environment. And FM5 failures discovered late in the silicon level lead to the UG cost increase due to the revision, so it remains a big problem to be solved in the design verification field. In this study, the biggest reason we introduced the methodology of ISO 26262 and created the design verification methodology called SFA was to find vulnerabilities that could cause FM5 failure through systematic analysis. To this end, in order to determine what external elements that have a dependency that can affect each function and what kind of interference they cause, and to check whether there is a vulnerable part that can be affected by the external interference with the function. As follows, I created a correlation table and hardened this function list. So, 1. Correlation table. The correlation table shows a list of incoming access that can occur during function operation and outgoing access that a function can affect externally. Through this, the dependency relationship with the external element can be identified when each function is operated. And a DFA, dependent failure analysis, analyzes whether there is a problem due to the dependency between functions can affect each other by referring to the correlation in the table below. Table 2. Example of a correlation table. The hazardous function list. The table below shows a function in which time critical corner case works, such as the FM5 failure case. Corner most empirical so far, and the function listed below. It can be seen that functions including state in transition have a critical sequence in which external inference is not allowed, and the many vulnerabilities have occurred in this part. The critical sequence of hazardous functions with such vulnerabilities should be identified in advance through the impact analysis at the design stage and included in verification requirement. Table 3. Hazardous function list. According to the FM5, items can be in the failure mode by assuming that the incoming access of the correlation table for the above hazardous function is interference occurring in the critical sequence. The risk assessment process. Risk in ISO 26262 is evaluated by the severity and probability of the failure. However, in SFA in the design verification stage, risk refers to the possibility that fatal systematic failure occurs at the silicon level. To evaluate this level of risk, we defined the following risk factors at the architecture and design stage. 1. Proven in the use level. If the IP-related function operation in the failure mode is a new IP that has not been used before, or is modified to add a function, systematic faults due to design errors are highly likely to occur. In order to evaluate the risk, the following proof in the use level was reflected in each failure mode. Table 4, proven in use level. 2. Severity level. In order to indicate the severity of systematic failure defined in the failure mode, it was just classified into severity levels as follows. In the case of S4, it means the most severe in the most severe state in which the entire system falls into the disabled state due to the occurrence of the failure. And A3 means that the function failure into impossible state due to failure, but the rest of the system is operable. Table 4. Severity levels classification. 3. Known issues in other projects. If it indicates whether the systematic failure defined in failure mode has a history of the causing bugs in the other project, this is to check whether the bug has been properly corrected or avoidance method has been properly applied. This includes the content of Errata notice provided by the IP provider. In general, the Errata notice provided by the IP provider has a very rare condition, but we consider this as one of the risks to be checked in the design verification stage and verified whether there is a risk in our system. 4. Applicable workload. Indicate whether a systematic failure defined in the failure mode can be avoided by the software workaround. However, software workaround always affects the performance or function, except there when a backup IP or logic is prepared or another function can be replace the failure occurrence function. This item is determined by the software engineer, and the software engineer records the software high-level function related to the failure mode in FMEA form for the first software FMA. Table 4. Applicable workaround. 4. Risk definition of SFA. The risk level of the failure mode in SFA is calculated as follows through the risk point of the item shown above. Figure 1. Calculation of risk level. Using the risk level obtained in this way, we created a new SFSL. Simulation failure severity levels as follows. IS 26262's ASIL automotive safety integration level indicates the functional safety level guaranteed by the system, but the SFSL indicates the risk of the fatal failure. We can determine which failure mode to prioritize verification by using the SFSL obtained through the risk assessment process. In addition, additional verification of the effect that may occur due to the failure is also performed by referring to the SFSL. The table 6. Definition of SFSL level. SF level. Okay. The FMEA, failure mode and effect analysis. FMEA is one of the safety analysis methodologies of ISO 26262 to analyze the effect of the failure mode on system function. In SFA, FMEA is used to analyze how critical each failure mode is. The following show the result of FMEA conducted by SFA. The systematic failure mode obtained from the function list and the final risk level calculated by the risk factor make it possible to easily identify the expected weakness of the design to be verified. Figure 2. Example of FMEA. DFA, dependent failure analysis. DFA is performed to investigate the effect of the failure modes defined in FMEA on each other. Dependent failure is a failure that is influenced by the other failures than the failures that occurred independently. Dependently failure definition in DFA can be classified into cascading failure and common cause failure as shown in the figure below. Cascading failure of an element resulting from the root cause and then causing a dependent failure of another element or elements. Common cause failure, dependent failure of the two or more elements resulting directly from a single specific event or root cause. The figure 3, type of dependent failures. There are two things we want to check through DFA. check whether the failure mode defined in FMEA can be dependent failure in initiator DFI that cause a cascading failure. Check whether a common cause failure occurs in the multiple elements due to the fault generated and a shared resource through the fault injection. First one, cascading failure caused by failure mode of FMEA. In order to check whether a failure mode defined in FMEA can act as a DFI that causes cascading failure in the other elements, it is necessary to identify the components and functions affected by this failure. To this end, we were able to figure out the dependency relationship between the functions of each component using correlation table used in FMEA. 2. Common cause failure caused by the fault injection. In ISO 26262, the fault injection is used for DC, diagnostic coverage measurement, which indicate how much generated fault can be detected by a safety mechanism. The SFA generator DFI can occur due to the random hardware fault by generating a fault in shared resource using backdoor interface of the memory. The common cause failures checked here are as follows. Where the failure occurs due to the DFI in a multiple component accessing shared resources, and whether normal recovery is possible through error detection logic. When a component is operating error handling due to a fault occurring in the shared resource, check whether failure occurs in other components due to the coupling factors. This content has already been covered in ISO 26262 independent failure analysis using PSS presented in DVCon US 2019, and we perform a fault injection using the backdoor interface to the shared resource below. Uncorrectable ECC error injection manipulates data in a shared region to generate ECC error when accessing. MMU translation fault generation manipulated the valid field of the MMU pages descripted to be invalid, causing a translation fault to occur during the table walk for the address. The RSA injection for CPU. The interrupt controller system MMU. The RSA, reliability, availability, and serviceability extension in ARM's error handling is a recovering architecture that is applied from the IARM V8 architecture. So RAS has its own fault injection model extension that can inject fault into L1, the L1, L2, L3 caches to generate error interrupt. So the DFIs generated by fault injection listed here are random hardware fault, but the logic to avoid this kind of a random hardware fault in generally apply to the design stage. We performed verification using this fault injection to find systematic failures that may occur during fault handling of the corresponding logic. The coupling factor that can cause failure in other elements in the fault state caused by the above DFI are as follows. 1. Force sharing access. 2. DVM, distributed virtual memory transaction broadcasting. So exclusive access. We created a fault injection model in the PSS environment to check whether the failure can occur in other elements due to the coupling factor in a state where a fault occurred in the shared region in the recorded result in the form of the FTR as follows. This fault model is used not only for design verification but also the verification of the recovery operation in software. Figure 4. Example of FTR, fault tolerance report. The DFA result for the above cascading failure and common cause failure is included in the SFA result in the form below. The figure 5 is example of DFA result. The systematic fault model generation using machine learning. We were to obtain failure mode with complex conditions with a high risk expected through the FMEA and DFA. However, it is very difficult to reproduce systematic failure that occurs at the moment when the specific condition of planability of the element is satisfied in the design verification stage. This is because the failure mode is a form that cannot be recognized by method that verify the expected output the input. Until now, this type of failure was mainly discovered through the long-term random test at the silicon product level, which increases the semiconductor design cost due to the mask revision. In order to create a fourth model to reproduce this failure mode, we needed an environment that could generate each operation of each element at a precise time we wanted. In DVCon US 2022, we have already presented the process of finding the time when the desired condition occurs by inserting a configurable delay using the ML algorithm. Just TB structures of a systematic fault model. As shown below, the functions are executed at the same time from the software point of view, but in the actual hardware, they are operated in different times. Configurable delay compensates for this difference. Figure 6 is concept of the ML-based PSS action sequencer model. The figure below shows the delay counter to count the configurable delay in the test bench. There are two regions not for implementing delay in software. First, the minimum unit of delay can be generated in software is microsecond. We need to delay the counter with the clock cycle resolution because we need to detect the cross condition of the hardware event. And secondly, in the case of the hard software delay, the applied delay time may change depending on the state of the CPU cache and instruction pipeline. In order to apply the ML algorithm, which will be discussed later, the applied delay must have a linear characteristic. On the other hand, the delay counter implemented in specific code in the test bench performance counting every rising edge of the clock. And when a delay count as much as the requested number of the clocks is completed, an interrupt is generated to the CPU core requested the delay. So the requested delay value and the actual delay have a linear characteristics. Figure 6 is a concept of a ML-based PSS action sequence model, and figure 5 is a delay counter. And the figure below shows how to detect the target condition, how to store in this target condition and how to store the information. The output monitor checks whether a preset target condition occurs and a corresponding condition occurs. The simulation time information and target condition information is exported to a simulation log. After the simulation is finished, the output log goes through the phasing process and is saved in a separate output repository. Figure 8 is output monitor of output repository. The last shows the CPU software that executes the function. We inserted an action called PSS delay in front of each function using the PSS tool and performed the simulation by generating software codes with the different delay values. The PSS delay action transmits the delay request to the delay counter of the test bench through a separate mailbox interface as shown in the figure and waits for the interrupt from the delay counter. The figure 9 verification of ML-based PSS action sequence model. Machine learning implementation. Before applying ML, it was repeated to set a delay set and run the simulation and adjust the value again according to the result. This was an inefficient operation that required a lot of time and human resources. To improve this, apply to the linear regression algorithms, which is the most basic algorithm of ML. First, create a code to a certain range of delay values of function A and function B, and conduct a simulation. Examine the simulation timestamp value where the target condition occurred for each. For one, a coordinate can be created by the combination of the input delay values and the simulation timestamp where the actual function is executed, and the linear regression for function A and function B can be obtained using the obtained coordinate. Through this, we can predict the simulation time at which the actual target condition occurs according to the delay values. If the extended Euclidean algorithm is applied to these two linear equations in number of combination of delay values of function A, function B having a common simulation time step values are obtained. Figure 10 extended Euclidean algorithm for the Diophantine equation. The extended Euclidean algorithm find the greatest common divisor of A and B as well as X and Y values that satisfy the equation. The solution obtained in this way is called a particular solution, and using this, a general solution can be obtained in confined and numerous combination of X and Y depending on the integer value k. Figure 11 is the result of extended Euclidean algorithm. However, unexpected external factors that affect the delay values may occur in the actual system, and this may break the linearity between the input delay and the simulation timestamp where the target condition occurs. To compensate for this, we perform the learning on only one on data with a linearity in the analysis stage through the ML flows as shown below the corrected result value through the ML algorithm. Figure 12 is ML sequence modeling. As a result, we were able to obtain a verification code to can produce the weak target condition through ML-based regression only by setting the target condition that each element should have. For SFA result export to ISO 26262. The result of the SFA obtained through the process so far are as follows. Like this, figure 13 is the result of SFA. The above results were classified according to the verification work project required by ISO 26262-A 2018 9.5. Looking at the contents, it can be seen that most of contents are covered by existing design verification. In particular, in the case of the coverage report, new cross function beans between the dependent elements that were not previously covered were added through correlation table, the risk factor analysis, and DFA. In addition to through the ML algorithm-based fault model, the critical sequence condition of the hazardous function could also be covered through simulation. In the case of a CPU, it was possible to increase the number of functional coverage beans by about 15% only for high-risk items of SFSL-B or higher through SFA. The result of the SFA are used in the risk management process for systematic fault in the safety analysis process of ISO 26262, and it is used to create FMEA report required by ISO 26262 by adding the failure rate and a diagonal coverage result for random hardware failure to the FMEA and DFA reported of the SFA. What we want to show here is the activities we have been doing in the design verification field to prevent the systematic fault can be independently applied to and utilized to standards required design reliability such as ISO 26262 and ICE 61508. Through the SFA, this could be the key to simplifying the requirement-driven verification process, which has recently been attracting attention. 5. Conclusion. As the density of the semiconductors increases and the complexity of their function increases, systematic failures with the complex conditions were not detected in the design verification stage are more often found at the silicon product level. We thought that in order to detect the systematic failure in the pre-silicon design verification stage, an inductive bottom-up approach is needed to find and analyze the risk factors from the smallest functional unit and broaden the scope to find system vulnerabilities. In this paper, we introduce a HARA, hazard analysis and risk assessment and safety analysis methodology used in ISO 26262 to the design verification field and use it to measure the risk of each element of the target design. We found risk factors that can represent the level of risk for detailed times. And through the FMEA and DFA, it was possible to easily see the expected design vulnerabilities by classifying the risk factors that could affect the system level. To verify the expected design vulnerabilities, a system fault model was created using ML algorithms. Through this, it was possible to verify the time-critical corner case, which has been difficult in silicon so far. ISO 26262 does not suggest a new verification methodology for systematic failure covering in the design verification. However, ISO 26262 requires a persistent impact analysis and a risk assessment in every stage. This is because all failures start with minor faults, and it is important to predict and prevent them in advance. Systematic failure dealt with in our design verification field are especially caused by human errors in the design process. To prevent this, we established 2 months of a more rigorous risk assessment and risk prediction process will become an essential element for semiconductor production requiring high reliability in the future. This is a reference, and thank you for your time. Today, I read the DVCon paper, Early Detection of Functional Corner Case Bugs Using Methodologies of the ISO 26262. Thank you again. See you next time.